This example shows us how to perform material balances around a chemical reactor in which a liquid phase equilibrium reaction takes place. Imagine we have a liquid feed at a flow rate of 10 liters per second, which we will call V dot N. The density of this solution is 1.1 kilograms per liter. And in this feed we have four components given the following concentrations. For component A, its molar concentration is 1.0 moles per liter. For B, it's 3.0 moles per liter. For C, it's 1.0 moles per liter. And for D, it's 0.5 moles per liter. The reaction proceeds as 2 moles of A plus 1 mole of B are in equilibrium with 1 mole of C plus 1 mole of D. An equilibrium constant given for this reaction is a value of 1.5. We're also given that the outlet density of this solution is 1.0 kilograms per liter. The first thing we want to do is determine the molar flow rates of each of the components entering the reactor. To do this, we'll take their respective concentrations and multiply it by the volumetric flow rate. For instance, the concentration of component A in the feed is 1 mole per liter, and by multiplying it by the flow rate of 10 liters per second, we end up with 10 moles per second as the flow rate of A going into the reactor. Similar calculation for B would give us 30 moles per second. And for component C, we'll have 10 moles per second. And finally, for component D, we will have 5 moles per second. Let's do a material balance around this reactor where the mass flow rate is being considered. We can do this by looking at the volumetric flow rate of the total feed coming in at 10 liters per second and multiplying it by the respective density, 1.1 kilograms per liter. And that turns out to be 11 kilograms per second. At steady state, this is also equal to the mass flow rate out leaving the reactor. We can calculate its volumetric flow rate by using that mass flow rate out of 11 kilograms per second and dividing it by the density of the outlet of the reactor, in this case 1.0 kilograms per liter. And we will determine that the volumetric flow rate leaving the reactor is 11 liters per second. Let's do a molar balance for component A around the reactor. Its flow rate leaving the reactor will be equal to its flow rate entering the reactor minus 2 times the reaction extent. By dividing that equation by the volumetric flow rate out, we will calculate actually the concentration of A leaving the reactor in moles per liter, which will be given to us as 10 moles per second divided by 11 liters per second minus 2 times the reaction extent divided by the volumetric flow rate out. And we can do the same thing for the concentration of B, C, and D leaving the reactor, so we can calculate their concentrations as well. Let's now put in numbers for the flow rates and the volumetric flow rates for each of the components, and we have calculations for the outlet concentrations of A, B, C, and D. Now we want to determine what is the maximum in value of the reaction extent divided by the volumetric flow rate leaving the reactor. That will occur when each of the components could be 0. So we'll set each of the 4 equations equal to 0. For that to occur, the extent over the volumetric flow rate leaving the reactor for component A is a 0.455. That for B is 2.73, C is negative 0.91, and D is negative 0.45. Therefore, the maximum extent that we can have for this ratio is 0.455, and the minimum is negative 0.45. Now we're going to solve this problem. Let's look at our equation for our equilibrium coefficient. and that will be equal to the concentrations of each component raised to the respective power for the stoichiometric coefficient. And that's given to us on the screen right there, where we have concentration of C times that of D divided by concentration of A squared divided by concentration of B equaling 1.5. Let's make a table and enter values for the reaction extent of the volumetric flow rate and see how these concentrations will calculate into equilibrium constant calculation.